So what I wanted to do, I want to do a problem dealing with the idea of energy levels. A square well. I've got a particle and an electron that's trapped in a square well. We're going to give it the square well a length of 1 times 0, 0 times 10 to the negative 9, a nanometer. Okay, can you guys see that? Yeah, 9 nanometers. Okay? So 1 times 10 to the negative 9 nanometers. Now that is not nanometers, that's 1 nanometer. I've got an energy level of 3 and I've got an energy level of 1. So let's say I have an electron, 1, incoming photon. It's going to strike that electron and it's going to energy level 3. From there, well, the problem I have is what frequency of light do I need in order to do that? Well, there's a couple of concepts we need to start with. The first one is the energy of a photon. Okay? Hopefully you all remember that the energy of the photon is going to be equal to the Planck constant times the frequency. And the other concept we need is the energy of the well. Now that is going to be a little longer. N squared, h squared, divided by the mass times the length squared. Okay? So energy in a square well, energy of a photon. So what I have here is an energy level 1 and I have an energy level 2. The photon need the exact same amount of energy as this space right here between N3 and N1. So what I'm going to say is I'm going to say the energy, use the red color chalk for that, the energy of 3 minus the energy level of 1, space right here, is equal to the energy of my photon. Now, I'll just put a P right there. Okay? The energy level N3 is going to be okay? That's how that equation breaks up. Energy level of 3 minus the energy level of 1 equals the energy level of photon. Now, h squared, or h, the Planck constant, 8 times the mass of the electron, the length, all those things are constant for this equation. So what I'm going to do is I'm going to get all of those combined at 1, and I'm going to end up with this. Okay? So this squares. So this is going to be 3, 9, minus 1. So you're looking at 9 minus 1 is 8. Okay? So this term turns into an 8. Darken that a little bit. H squared divided by all this stuff as a constant is equal to h freaking. Well, this being 8, this being an h, and this being an h, what I can do is I can cancel out that and that. Okay? Let me use red. Goes away, and that term goes away. Okay? This goes away, and this goes away. Okay? So at that point, all I'm left with, and I'm going to erase this section right here. Okay? That. Okay? So I have Planck's length. Now there's a little bit of schmutz right there. Let me see if I can get rid of that for you. Okay? I've got Planck, the Planck constant divided by the mass of the electron times the length of my square well squared, this length right that was in the picture, is equal to the frequency of my light. Okay? That's simple. Now, if this was some other number, obviously we're going to have a constant floating around here. Now, if I went up to 2 instead of 3, then you're going to have 4 minus 1. You're going to end up with 3, and 3 doesn't necessarily go well in 8 with 8. So you would end up with having a 3 8s out here. Okay? If we were only to go up 1 energy level, if we were supposed to go up 4 energy levels, you're going to get 16 minus 1. So that gives you 15 divided by 8. And that would go in right here. Okay? Cool? And that's all you would do to determine that frequency of the light coming in to elevate that electron up to the higher energy level. Now, you could do it in reverse, just the same way. It starts off with this energy level, works its way down to this energy level. The amount of energy that it would give off, a frequency of light it would give off going from here to here, is going to be the same. It needs that much light, that frequency of light to get up to here. It loses that much light, that same frequency, to go from here back down to here. Okay? So that's just an example of using, excuse me, my brain is fried, using energy levels to determine frequencies of light. Cool?